Hello, my name is Alex Kluwer. Today I'm going to be deriving a formula for critical length, and I will show that the online formula for critical length, the wavelength over 20 is equal to your length critical. That's actually only a special case whenever your transmission line is impedance matched. And we have to be aware of that because if our circuit is not impedance matched, then the critical length will be much, much less than what we calculate it to be and that we choose or use in our design for constraints. And the circuit that I'm going to be deriving this for is going to be a AC sine wave or AC source. We're going to call that PS. And that source is tied to a transmission line. And that transmission line has a characteristic impedance Z0 with a length of L. And that transmission line is going to be tied down back to the source with a load impedance ZL. And if we remember, we can remember that we can look into the circuit here and look at that input impedance. And that's what we're going to be using. We're going to be using that input impedance to find our critical length. And we remember that Zn is equal to Z0 multiplied by ZL plus J Z0 tangent of beta L over Z0 plus J ZL tangent of beta L. And that's going to be for a lossless case. And you can look up that equation. It's you can probably look up something along the lines of Telegrapher's equations, and you can find that. We will start by substituting Z0. We're going to set that to equal to a constant, and that's multiplied by ZL. And we will rewrite this as Zn equals A times ZL multiplied by ZL plus J A times ZL tangent of beta L. And that's going to be over A times ZL plus J ZL tangent of beta L. And as we can see, that the ZL there goes to 1, that ZL, and that ZL cancel. And we will rewrite this as Zn equals A times ZL multiplied by 1 plus JA tangent of beta L. And then it's over A plus JZL, or sorry, J's tangent of beta L. And we want to get rid of this A right here. So we're going to pull an A out of the denominator. And we will get ZL multiplied by A, and we'll pull that A out of the denominator, and we will get that. And the numerator just stays the same. And as we can see, the A's cancel, and Zn becomes equal to ZL multiplied by this part. And I'm going to add some more paper. Add a few sheets. And let me fix this real quick. And if we remember, the critical length is basically a parameter or a point at which this circuit behaves as if this transmission line here doesn't exist. So what we can mathematically say that as Zn becomes approximately the load impedance. So basically, if all the source looking into the system sees is the load, then that interconnect looks transparent is what they use. They say the interconnect looks transparent as if it doesn't exist. And you won't have signal integrity issues at that point because it pretty much the wave travels so fast that it bounces back and forth so quickly before a wavelength occurs that it pretty much looks like traditional circuit theory. And we will define that as Zn becomes approximately ZL. And if we want that to happen, we can see that we want this part right here. We want that part equal to 1. we want that part equal to 1, and then Zn becomes approximately Zl. And as we can see, this is a complex number. So what we'll be interested in is taking the magnitude of this part and then approximately making that equal to 1. And we will do that. We will do 1 plus j a tangent of beta L, and that will be over 1 plus j 1 over a tangent of beta L. And that's going to be equal to Zn over Zl. And then we will take the magnitude of that. So if we remember the magnitude of a number, let's say Z, we will take the square root of that number multiplied by its complex conjugate, and that will give us the magnitude. And we will do that here. And we will set that equal to a big thing. That'll be multiplied by 1 plus j, or sorry, complex conjugate. So complex conjugate is going to be everywhere there's a j, instead of a positive j, it'll be a negative j, and if it's a negative j, it'll be a positive j. So you basically just flip this on. And that'll be equal to, as we can see, if we follow these out, we will get 1 plus a tangent of beta L, and that's going to be squared. And then that'll be over a similar thing, but instead of a, it'll be 1 over a, and that's also going to be squared. And we can see that if we can go about doing this by stating that each one of these are less than, much less than 1, but we will get 2 cases. So we'll get a is greater than or equal to 1, and we'll get a is less than or equal to 1. And in this case, that a is greater than or equal to 1, we will want a tangent of beta L, this square part, much less than 1. And we can see that if this is the case, if this up here is the case, where this part right here is much less than 1, since the part down here is multiplied by 1 over a instead of a, then it'll be much smaller than the numerator part. So if the numerator part is much less than 1, then the denominator part is going to be much less than that. And that's why this assumption works. And similarly, for the a less than or equal to 1, it'll be the bottom part that we're setting this equation to instead of the numerator part. And we can then very easily solve this. We'll solve it by first setting what, instead of a much less equal sign, we'll have a equal sign. And what we'll choose is that each part of this is equal to 1 over 10. And we will do this one at the same time. So it'll be equal to 1 over 10. And we will draw our line kind of down here to split the two. And we can take the square root of both sides. And if we remember that for tangent of x, it becomes approximately x if x is much less than 1. And if we look, beta L, where beta is the wave number, so it's going to be 2 pi over the wavelength. So like I said, we want the length to be much less than the wavelength, and that means that this beta L is going to be much less than 1. And that's what we want. And that means that this approximation can work. And we will continue our line, and we'll say that this tangent beta L becomes approximately beta L. And that's going to be 1 over the square root of 10. And in this case, it's going to be beta L over a equals the 1 over square root of 10. And then we will, so now this length is actually our critical length. So this length, this L here, is going to be the length at which this approximation basically stops working, kind of thing. So we'll solve for L, and we will do 1 over a beta square root of 10. And then on this side, it's going to be L equals a over beta square root of 10. And give me a second. Okay, so what we can remember that beta equals the wave number, so it's 2 pi over the wavelength. So we will substitute that in, and we will get wavelength over 2 pi square root of 10 times a on this side. And then we will get L is equal to the wavelength times a over 2 pi the square root of 10. And if you plug 2 pi square root of 10 in a calculator, it gives you basically 20. So to make this a little bit neater, we will say that these are approximately equal to wavelength over 20a on this side, and then this is L is approximately the wavelength times a over 20. And we want to put our constraint, so this is a is much less or greater than or equal to 1, and then on this side it's a is less than or equal to 1. And if we remember, that's the case. Okay. So that's our two formulas for critical length. And if we look at these, so what the internet gives you is it gives you the wavelength over 20 is equal to the critical length. It's actually not that. So it's this wavelength over 20 appears, but it's multiplied by this ratio. So the ratio A is actually equal to the Z naught over ZL. So if we have an impedance match, so where ZL is equal to Z naught, then we get this online formula. But if we don't have an impedance match, like in the case of we have a, let's say we don't know anything about PCB signal integrity, and we have a microcontroller, and this microcontroller, we hook a wire up on the PCB, so a track we hook up from one of those GPIO pins, and we hook it up to another microcontroller, for instance. Let's say we want to send it like a certain control signal or something. And that, regardless of us not knowing that the PCB track actually has a characteristic impedance, it's going to have some impedance, and it's probably going to be on the order of under 100 ohms. And that GPI, that pin on that other microcontroller that we're sending this signal to is going to have a very high impedance, much, much larger than 100 ohms. So what happens is A goes very, very small. And if we use, let's say we learn a little bit and we learn that this critical length appears, so we try to use this wavelength over 20 as our critical length and keep that track at below this length. If we ignore this ratio, then it's going to be much, much less than what we calculated it to be. So we should be using these formulas up here instead of the formula down here. We shouldn't be using this unless we have an impedance match case. So to prove that basically these are the correct formulas, we'll do an LT-SPICE simulation to prove it. And what we will do in the LT-SPICE is we're going to set up the exact same thing. We're going to set up an AC voltage source. It's going to be tied to a transmission line with a characteristic impedance of Z naught. It's going to actually have a propagation time instead of a length. So we will solve for that. It'll be tied to a load impedance of ZL, and these are going to be connected. And what we'll do is we will look at the input impedance here. We're going to look at the input impedance. And to do that, if we remember Ohm's law, voltage equals IR, then the input impedance is going to be R equals V over I. And what we can do is set this AC generator to an AC analysis, and we're going to set it to 1 volt. So if voltage equals 1 volt, then R becomes 1 over I, and that's just the same as the conductance. The input conductance is equal to I, because what we will be doing is measuring the current running through this generator to look at the input impedance, or input conductance in this point. And we will then need this propagation time. So we're going to need this number. So if we remember that the critical length, so length critical, is equal to two solutions. It is going to be wavelength over 20 multiplied by this A thing. So it's going to be wavelength over 20 times A for A is greater than or equal to 1. And it's going to be wavelength times A over 20 for A is equal to or less than 1. And we can see that if we divide length critical by U, then what happens is that we get wavelength over 20 A times U, and we're going to get wavelength times A over 20U. And what those become is it becomes 1 over 20 A times the frequency that we put into it, and we're going to have A over 20 times the frequency. And this will be the case for A greater than 1 or equal to 1, and we're going to have this for the case, same case, so there it's less than 1. And this will be equal to our prop time at the critical length. And I will show you the LT-SPICE simulation. This is the LT-SPICE simulation where we have a 50 ohm characteristic impedance. In our first thing, we're going to compare it to two cases. And we're going to have our AC function generator. It's going to have a 1 volt amplitude. And we have this ZL of 1K and then Z0 of 50. And if we look, if Z0 is equal to 50 ohms, ZL is equal to 1K ohm, and then if we set T prop is equal to 16.67 picoseconds, then we can plug and chug into our formula. Well, let me get my calculator. And we can put this into it. Remember that A is equal to Z0 over ZL. And A is going to be 50 over 1,000. And that means that A is equal to 0.05. And that means that A is less than or equal to 1. So it'll be 0.05 over 20. And if we want to know the frequency at which this is going to be, it's going to be good for the critical frequency thing, we can just move these around so we can swap the frequency out for the T prop. So we should just divide this number again by the propagation speed. So we will do 0.1667 nanoseconds, and that will give us the frequency in gigahertz. And then if we multiply by 1,000, it gives us frequency in megahertz, which means that we get 150 megahertz, at which this prop time should be good for our critical length. And we can then run our simulation. So we will do this, and what we will be looking for is, like I said, the input impedance. So we measure the current running through this function generator. And we can see that this axis is decibels, it's negative, and it gives us a conductance, because if we remember the current running through this function generator, the conductance, or it's also the same as the conductance, it's not the resistance. What we can do is do 1 over the conductance to find the resistance, which on this scale will actually just be multiplying it by -1, which will flip it. So if we go to 150 megahertz, which is about right there, and we look at what that impedance is. So if we do 59.58 and we it's negative 59.58, so we multiply it by -1 to get the reciprocal, and then we divide it by 20, because we remember that 20 times the log base 10 of the input impedance is going to be this decimal number. So we divide it by 20, then we raise it to 10, and we get 952.8. And that's the input impedance at this frequency. And we can see that what we loaded it down with is a kilo ohm. So that's going to be within 5%. It's going to be within 5%, which is probably good enough. And we can see that this is pretty much the point at which it starts going off this kind of runaway effect, where our input impedance is not going to be the same as our load. And we will compare this to the same scenario, but instead of 1 kilo ohm, we're going to do a mega ohm. And then we'll do a third case where it's the same as the first case, except now instead of 16.67 picoseconds, it's going to be 16.67 nanoseconds. And basically, both of these were chosen to show the effect of that formula whenever you multiply the load impedance by 1,000 or multiply the prop time by 1,000. And we can see that if we look at this one, then we expect, so our initial thing was negative 120 dB, and we expect the critical frequency to go down by 1,000. So instead of 150 megahertz, it should be 150 kilohertz. And if we go to 150 kilohertz, which is about right there, and we take that negative 119.58 and we multiply it by negative 1 to get 119.58. Divide it by 20, raise it to 10, we find it to be 952 kilo ohms, which is also within the 5%. And if we do the same thing for the third case, and we go, we expect it also to be 50 kilohertz, because now the prop time was multiplied by 1,000 instead of the load impedance. And it's 59.58, and we multiply it by negative 1, again, divide it by 20, raise 10 to that number, and we get 952. And if we divide it, subtract it by 1,000, divide it by 1,000, we can get the percent difference, and it's also 5%. So we can see that the prop time and the load ratio have this equal effect in this critical frequency. And if we do a transient response, we will see that there is a distinct difference between the two. But if we're just looking at input load impedance, then they have distinct characteristics. And I think that's pretty much it. So, doing the transient solution, we can do the exact same setup as we had before, where we have a case one with the critical frequency, so 150 megahertz we're going to put into this thing, and we're comparing it to the other two cases where we're going to put 150 kilohertz. And what we see is that if we look at the source voltage, which is this sine wave, and we compare it, they overlap. So what happens is that the transmission line effects are negligible on the signal. So that's just proves that the input impedance is close enough to the load impedance that we don't see those effects. Now we're going to compare them, or that, to what we see whenever we do the second and third cases. And we also see that, wait a second, let it simulate. We also see that they overlap. So we can compare this to the third case, and they also overlap. So that shows you that as long as you are below this critical frequency, the transmission line effects are negligible. Okay, I think that's it. Thank you. Bye.